Hi, I'm Professor Kelly, and this is a lecture on list comprehensions in the functional paradigm for CS/CI 308 Programming Language Design. The learning goals for this lecture are to write list comprehensions in Haskell, to explain how to use list comprehensions to map or filter, to implement list comprehensions with multiple lists or filters, and to employ comprehensions to write quicksort. List comprehensions come from set builder notation. Set builder notation is a powerful mathematical notation for defining a set by stating the properties its members must satisfy. Here's the basic syntax for set builder notation. It begins and ends with a curly bracket. On the left-hand side, we get the elements that are in the set, followed by a vertical bar that is read as such that, and then a list of properties those elements must satisfy separated by commas. The elements must satisfy all of those properties. For example, here is the identity set, the set of all x such that x is in the set E. This is a completely useless example of set builder notation because it simply returns all of the elements of the set E. Here's a more complicated example, the set of all x squared such that x is in the set E. This squares each of the elements of the set E and creates a new set of its squares. Here we take all of the elements of E that are larger than 2 and define a new set consisting of those elements. We can do both. We can take the set of all x squared such that x is in the set E and x is greater than 2. This will be all the elements of E that are larger than 2, and then those elements are squared to form the new set. List comprehensions are based on set builder notation. Instead of working with sets, however, they work with lists. In Haskell, list comprehensions take the form square bracket, elements of the new list, vertical bar, read as such that, and then variable, element of the original lists, and then a set of properties those variables must satisfy, separated by commas. Let's take a look at an example. This is the identity set again. We can implement this in Haskell using square bracket x, vertical bar, x, a funny looking arrow that represents element of, E square bracket. In other words, we're saying this is going to be the list of all x where x is an element of the list E. Python shamelessly stole list comprehensions from the functional paradigm. List comprehensions in Python look very similar to list comprehensions in Haskell and can do pretty much all the same things. This is again the identity list comprehension in Python. So if we assume that E is 1, 2, 3, 4, then the output of these list comprehensions will be, of course, 1, 2, 3, 4. List comprehensions can do more interesting things than just identity, fortunately. For example, we can use a list comprehension instead of the map by applying the function we want to apply to each element of the list on the left-hand side of the such that bar. For example, let's say we wanted to square each element of a list. We could do that using the map function, map square of 2, E, where E is a list, or we could do this using a list comprehension, where we square each x such that x is an element of E. We could also do this in Python. Python, in addition to stealing list comprehensions, also stole map, filter, and anonymous functions. Here we're defining in Python an anonymous function that squares x, and then we are passing that in as the first argument to the map function along with the list E. We could also do this in Python using a list comprehension. We can square x for x in E, where E is a list. Any of these will take the input 1, 2, 3, 4, and return the squares of 1, 2, 3, and 4, 1, 4, 9, and 16. More generally, we can apply a function on the left-hand side of the list comprehension. The set of all f of x such that x is in the set E. We could do this using a map or a list comprehension. And we can do this either in Python or in Haskell. We can also use list comprehensions to replace filter. We do this by applying the filter on the right-hand side of the list comprehension after getting the elements from the original list. For example, let's say we wanted the set of all x such that x is in the set E and x is greater than 2. We could do this using the filter function in Haskell, or we could use a list comprehension, putting x greater than 2 at the end of the list comprehension. Similarly, in Python, we could do this using a combination of the filter function and an anonymous function that checks to see if x is greater than 2, or we could use a list comprehension that again puts the x greater than 2 at the end of the list comprehension. So if we had the list 1, 2, 3, 4, this filter would filter out 1 and 2, leaving us with 3 and 4. More generally, given, say, the set of all x such that x is in the set E and p of x is true, where p is a predicate, that is, a function that returns either true or false, we can say filter pe, or we can say x such that x is an element of E and p of x is true. List comprehension is specifying essentially two conditions that x must satisfy. X must be an element of E, and that x must be something where px is true. We can also do the same in Python. We can do filter pe, or we can do x for x in E if p of x. We can combine map and filter functions using list comprehensions. For example, let's say we wanted to create the set of all x squared such that x is in the set E and x is greater than 2. We could do this using both map and filter in Haskell, or we could do this a little bit more succinctly using a list comprehension. Similarly, we could do this quite long-windedly using a combination of map and filter and a pair of anonymous functions in Python, or we could do this more succinctly using a list comprehension. Any of these operations will take the list 1, 2, 3, 4 and return 9 and 16. That is, they will remove 1 and 2 because they are not greater than 2, and then take 3 and 4 and square them to get 9 and 16. What if more than one list? Well, list comprehensions can actually take more than one list as input. Suppose we wanted the set of all x plus y such that x is in the set E and y is in the set F. We can define this in Haskell as x plus y such that x is an element of E and y is an element of F. We can do the same in Python using very similar notation, x plus y for x in E for y in F. Now, it's important to note that when applied to the list E and the list F, one does not get an element-wise sum of the two lists. Instead, one gets all possible sums of x and y, which is a much longer list. What if we wanted more than one filter? List comprehensions can have more than one filter. Suppose we wanted the set of all x such that x is in set E and x is greater than 2 but less than 4. We can do that. We just separate extra filters by commas. Python separates them by ifs. So if we have 1, 2, 3, 4, we can apply the filter and get 2 and 3. That is, the numbers bigger than 1 and smaller than 4. List comprehensions are very powerful. Earlier in the course, you saw this definition of quicksort. We start off by quicksorting the empty list, which is simply the empty list. And then we want to quicksort a list which has a head and a tail. This is where list comprehensions come in. We can quicksort the list by using list comprehensions. We apply quicksort to a new list, which is defined as a list comprehension of all x, where x is an element of tail and x is smaller than the head. We can concatenate this onto the front of the list ahead of the head. After the head, we use another quicksort and another list comprehension. This list comprehension takes everything bigger than the head. And this allows us to take any list and sort it. Learning goals for this lecture were to write list comprehensions and explain how to use them to map or filter. To start off, when writing a list comprehension, if you have a map you want to apply, you apply it before the vertical bar at the start of the list comprehension. After that, you should define the elements of the lists that you want to use. There can be more than one list. And then apply any filters onto the list last. List comprehensions are highly versatile. You don't have to follow this exact format. There's a lot more you can do with them. But you won't go wrong using this general basis of thinking about them in terms of mapping vertical bar, that's such that grab the elements of the other lists you want and then apply filters. And you've seen how they can powerfully implement quicksort quite succinctly.